Welcome, everyone. This is the Semiconductor Photonics Graduate Certificate webinar, and my name is Erica Reed. I am the Program and Marketing Manager for the MSEE on Coursera program at the University of Colorado Boulder. It gives me great pleasure to introduce our special guests today. We have Professor Juan Park, Professor Juliet Gopinath, and Alan Su, who will now introduce themselves. Let us start with Juan.
Hello, my name is Juan Park. I am a professor at the Department of Electrical Engineering, Material Science and Engineering, and Biomedical Engineering program here at CU Boulder. I got my degree in physics from Georgia Tech in Atlanta, Georgia. And then I worked a little bit at the Georgia Tech Research Institute before I joined the faculty here at CU. My research area is in photonics and specifically nanophotonics. And I am the instructor of the specializations that we will introduce, two of the specializations that we will introduce today, semiconductor devices and quantum mechanics for engineers. Now I'd like to turn this over to Juliet.
Thank you, Juan. My name is Juliet Gopinath, and I'm a faculty member at the University of Colorado Boulder in both electrical engineering and also physics. I'm a fifth-generation engineer, and I've been interested in science and math from a young age. So I studied electrical engineering at the University of Minnesota. Afterwards, I applied to the electrical engineering program at the Massachusetts Institute of Technology and began my graduate work. At MIT, I had a chance to be part of a world-renowned ultrafast optics group. I studied the dynamics of electrons and holes and semiconductors with light, and I was blown away by how much you could learn. When I graduated, I took a job at MIT Lincoln Laboratory, where I built high-power lasers, including semiconductor lasers. And in 2009, I had the opportunity to move to the University of Colorado Boulder and join the electrical engineering and physics departments. At the university, I run a research group focused on photonics. This falls squarely into the area of applied physics with appeal for both engineers and scientists. Recently, I've launched a photonics specialization on Coursera called Active Optical Devices. I'd now like to give the floor to Alan Su.
Thank you, Professor. Hello, everyone. My name is Alan Su. I received my Bachelor of Science degree in Mechanical Engineering from University of California, San Diego. I graduated with a MS in Electrical Engineering from CU Boulder back in June 2021. I'm currently facilitating the 3 courses for the Semiconductor Photonics Graduate Certificate, and I will be covering the Optical Engineering specialization today. Now I'll turn this back to Erica.
Thank you, Alan, and thank you, Professor Juan Park and Professor Juliet Gopinath, for introducing yourselves. And so now, before we get started, let's familiarize ourselves with the Zoom interface. To use the Q&A, hover your mouse towards the bottom of your screen, then click on the Q&A icon to type in your questions. Please do not use the chat function because we will be addressing your questions after the presentation during the Q&A session. However, feel free to ask your questions anytime, as long as it's in the Q&A. So here's the outline, and we'll start with the 2022 CHIPS Act, followed by an overview of the Semiconductor Photonics Graduate Certificate, and then we'll go over the 3 specializations within the graduate certificate, and a brief summary of the MSEE on Coursera program. And then finally, we go into the Q&A session where we address your questions. Without further ado, I turn this over to Juliet, who will start us off with the CHIPS Act.
Thank you, Erica. So in 2022, the US passed the CHIPS Act. And this recognized what we already know, but it put it into writing that the semiconductors are critical to the economy, national security, and technology. They have many, many applications that include artificial intelligence, quantum computing, and cloud services, among others. The CHIPS Act allocates $52 billion for manufacturing and research, and also features a 25% tax credit to incentivize semiconductor manufacturing. Importantly, it also calls out STEM education and workforce development. Recently, as part of the CHIPS Act, there was a call for $300 million center proposals focused on 7 topics that range from artificial intelligence to quantum computing. Researchers had to assemble diverse teams that include academia, government, and industry to focus on research that can be translated from universities to the mass manufacturing environment. It's important to note that the University of Colorado Boulder researchers are heavily involved in these teams. I'd now like to turn it back to Erica.
Thank you, Juliet. That was very informative and it's a very relevant topic. And here's an overview of the graduate certificate. You will need to complete 3 specializations, which is equivalent to 9 credit hours total. Each specialization consists of 3 courses. Each course is between 0.6 to 1.2 credit hours. We have the syllabus for every course listed on our website, and Carly will, she already put it on the chat. Thank you, Carly. And you just need to click on each course and the syllabus will be right there. And now I turn this over to Juan to talk about the first specialization, which is semiconductor devices.
Thank you, Erica. I will introduce semiconductor devices specialization, which covers the physics that governs the properties of semiconductor and some semiconductor devices, diode and transistor to be specific, which form the backbone of the modern semiconductor technology. The semiconductor revolution we have experienced in the past few decades is maybe best illustrated by the invention which fundamentally changed the way we communicate. Telephone looked like this when first invented. Now it looks like this. Mr. Bell would not recognize the present-day phones as his own invention. It is naturally so because the present-day phone is actually a completely different device operating with completely different mechanisms. If you look inside the phone, then you will find something like this, inside of which we have semiconductor devices. And these semiconductor devices are what enable this completely new invention and are at the heart of the technological revolution we have witnessed in the past decades. The semiconductor revolution that we have witnessed is so successful and so widespread that we find semiconductors everywhere. Not only do we find them in computers, tablets, and phones, we also find them in cameras, TVs, solar panels, lighting devices, and even in appliances and cars. You will find them at home, on the road, at grocery stores, and gyms. They're truly ubiquitous, and we can only expect that they will become more so in the future. This makes it a great time now to learn how semiconductor devices work, which our specialization on semiconductor devices is designed to accomplish. The specialization consists of 3 courses: semiconductor physics, p-n junction and metal semiconductor contact, and bipolar junction transistor and field effect transistor. In course 1, we introduced the quantum theory of solid and use it to describe the electrical and photonic properties of semiconductor materials. You will see that it is the quantum theory that unlocked the potential of semiconductors. In course 2, we cover the most basic type of semiconductor device, diode. There are 2 types of diodes, one based on p-n junction and the other based on metal semiconductor contact. We will also briefly discuss the photonic devices, such as semiconductor lasers and detectors, topics which will be covered a lot more in depth in the active optical devices specialization. In course 3, we discuss transistors, the device that forms the backbone of modern integrated circuit technology. We will discuss 2 types of transistors, bipolar junction transistor and field effect transistors, how they are constructed, how they operate, and what their key characteristics and limitations are. After completion of this specialization, you will have a firm grasp on how semiconductor devices work and a solid foundation to study more advanced topics such as active optical devices, photovoltaics, and integrated circuits. Here, I'd like to introduce another specialization, which is not part of the Semiconductor Photonics certificate, but would be beneficial to many students. As I mentioned earlier, it is the quantum theory that enabled the modern semiconductor devices, and an in-depth quantum mechanics knowledge is necessary for advanced semiconductor engineering. Unfortunately, most engineering curriculum does not include a quantum mechanics course, and the one offered in physics department usually contains topics that may not be directly relevant to many engineers. So we developed a quantum mechanics specialization specifically designed for engineers who don't have undergrad quantum mechanics background. In addition to the need for more advanced semiconductor engineering, quantum mechanics has recently emerged as an important field for engineers. This has to do with the future of semiconductor technology. While no one doubts that the semiconductor technology will be more and more embedded in our daily lives, the pace at which the technology is progressing may slow down. Over the past half a century, semiconductor technology has been advancing at a breakneck speed, as shown by the celebrated Moore's Law. The question, of course, is how to continue this growth. While it is unreasonable to think that the semiconductor technology will become obsolete in the near future, it is equally unreasonable to assume that this exponential growth will last forever. As the future of computing technology is actively debated, one promising candidate with immense potential has emerged: quantum computing. You may have seen this impressive photo of the quantum computer developed by IBM. By exploiting the quantum nature of microscopic entities such as electrons and photons, quantum computing can potentially perform tasks either impossible or very difficult for classical computers. The revolutionary computing power will accelerate the progress in the forefront of computer science, such as machine learning and artificial intelligence. In addition to computing, quantum information technology holds high promises for sensing and imaging that can enable new biotechnology and global positioning systems, for example, a new communication system that is fundamentally unhackable. While the promise of quantum information science is truly exciting, we must also recognize that the current semiconductor technology took decades of development since the first invention of transistor in 1947. It is likely that the quantum technology will also take many years, if not decades, to mature. And this development will surely require extensive engineering on materials, devices, components, and systems. Unfortunately, most undergraduate engineering curriculum does not include quantum mechanics, making it highly challenging to offer a meaningful graduate level education on quantum mechanics to engineers. This specialization is designed to address this need by providing both the foundational materials on quantum mechanics and more advanced topics relevant to the emerging quantum technologies. The specialization consists of 3 courses: Foundations of Quantum Mechanics, Theory of Angular Momentum, and Approximation Methods. In course 1, we cover the basic concepts of quantum mechanics, such as wave-particle duality, uncertainty principle, and the basic mathematical tools needed for quantum mechanics. In course 2, we discuss one of the most important physical quantities in quantum mechanics, angular momentum. We will start with the basic theory of rotational motion and develop a general theory of angular momentum, which is critical to the proper understanding of quantum states in many systems. In course 3, we will discuss various approximation methods commonly used in practice. Few problems in quantum mechanics have exact solutions, and we need approximation methods to tackle most problems. In this course, we will learn most widely used techniques, such as the perturbation theory. Upon completion of this specialization, you will not only have a solid foundation to learn modern semiconductor devices, but also we'll be ready to learn a wide range of most advanced technologies for computing, communications, and sensing. I now turn this over to Juliet to talk about the second specialization in the certificate, active optical devices.
Thank you, Juan. My specialization also consists of 3 courses. And today I'd really like to tell you about the magic of photonics and optics. I first fell in love with the field my junior year of college while studying electrical engineering. I realized that electromagnetic waves described something I could see, light. I haven't looked back since then, and I've really devoted my career to this area. Something as simple as a rainbow, or the color of the sky, or the fact that a double rainbow has the second one with inverted colors makes me get out of bed in the morning. I'll never forget the first time I saw the lab I chose for graduate school. The thought that one can use light as a strobe light to freeze the motion of not only horses jumping over a fence or bullets scrolling through an apple, but also to examine the behavior of electron and holes in a semiconductor is a concept that never ceases to amaze me. After I joined CU Boulder, I started teaching a course that actually Juan developed on active optical devices, and I really fell in love with it. The material is not only interesting, but it's useful. When I was on sabbatical, a colleague approached me about putting these courses on Coursera. My dad is from India, and I know I'm privileged to have had the educational opportunities that I have had. People in other countries, especially women, don't have these same openings to take courses in electrical engineering or to access higher education. And I wanted to put my courses online as a way to give back and increase access to these topics. In 2017, I began to convert the course to a Coursera specialization. The specialization is part of the Master of Science in Electrical Engineering program. In my mind, this is a really special offering. I'd like to tell you about the specialization in more detail today and why it means so much to me. My specialization deals with 3 main topics. 1, semiconductor light sources. 2, detectors for light. And 3, photonics displays such as the one you're using to view this webinar. So I'm going to start with the question I always ask myself these days. Why bother? This specialization will enable you to build the theoretical knowledge you need to understand and design semiconductor light sources such as light-emitting diodes, LEDs, or semiconductor lasers. You don't have to look far to find an LED. For example, a light, your phone, a billboard, or your car. LEDs are everywhere. In fact, Nakamura won the Nobel Prize for his contributions to the blue LED. Did you know that the semiconductor laser is considered one of the most successful technologies ever built? They were found for 6 cents in every CD player and for $1 in Blu-ray or DVD consoles. Of course, I've seen the danger laser radiation science in Klingon. That's one of the best parts of working in this field. But in all seriousness, we can use the light from these sources for communication, sensing, and imaging. The images and the sound you hear in this webinar today are carried by encoded light signals on an optical fiber. Look at your computer motherboard. There is an optical fiber port to plug into the Ethernet. Signals here are being carried by light. The big advantage here is that light has a lot of bandwidth. It can handle you talking on the phone, downloading a video, streaming a movie, and surfing the web, of course, all at once. Those old copper cables that used to carry all this data electrically don't have enough bandwidth to handle all these demands. Optical sensing is also important for understanding the environment. Examples include volcanic warning systems, understanding greenhouse gases, studying membranes that are used to produce water for millions, and other applications such as tracking objects. The big advantage to using light is that one can make a non-invasive sensor that doesn't touch the object and can operate from a distance. Imaging systems are used ubiquitously, and you require light to do so. You're looking at an image of my face on your screen, and we rely on microscopes to image tiny chips inside your computer processors. How does a camera take a picture? It images a scene onto a detector array. The specialization also focuses on ways to detect light from these light sources and turn them back into electrical signals. Light operates at really high frequencies, terahertz, or 10 to the 12th to be exact, and converting these down to DC is no simple task. We'll talk about the detectors that give eyes to self-driving cars through LiDAR, light detection, and ranging. We'll also discuss the detectors in your remote control electronics. And every time you take a picture or an image of a light beam in a laboratory, we need to use a camera, which has two main forms of implementation. Have you ever wondered what's inside your brain? I have news for you, 86 billion neurons that we don't understand fully yet. Optogenetics allows a window into the brain, but we have to use microscopes to understand the functionality of the most complex processor on the planet to date. Again, in order to image the brain, we need sensitive detectors. Finally, the last topic in the specialization, but certainly not the least, is optical displays. You probably spend most of your day looking at a display, whether it be a computer, phone, iPad, TV, or display in the car. We'll understand the differences in the state-of-the-art displays and where up-and-coming technology is going. So now I'd like to tell you about the field of semiconductor photonics, the topic of the active optical devices specialization, and how this relates to areas of global importance. The field is rich with career opportunities. Semiconductors are the key for many compact and inexpensive light sources, and also detection technology. Without them, we wouldn't be able to make compact and electrically pumped optical systems that include light sources and detectors. The COVID-19 pandemic has really highlighted the semiconductor chip shortage and the lack of semiconductor manufacturing facilities around the world. In order to make the billions of transistors inside your computer, cell phone, iPad, car, etc., we need to leverage the principles of the specialization. Transistors are patterned with light, short wavelength light, and that is key for the nanometer feature size. Imaging is done at every step of the way to inspect the processing, and debug is performed with laser illumination of individual transistors on a semiconductor chip. Climate change is constantly in the news. In Colorado, we had a pretty devastating fire a little over a year ago that burned almost 1,000 homes. And so this has really caused renewed interest in climate change and also green energy. Solar power is another critically important application of the technology discussed in the specialization. Unfortunately, it's not easy to harvest the energy from the sun. One has to find a material that absorbs all sorts of different colors efficiently. But using a specialized semiconductor detector, one can collect solar energy, and the specialization will provide you with the skills to perform such a design. Changing topics, virtual reality is generating a lot of career opportunities and excitements about potential products. It's a computer-generated environment with scenes and objects that appear to be real, causing the user to feel immersed in their surroundings. The key here is that the user perceives the environment through a VR headset or helmet. You can use a device like a video or image camera to create a 3D world that the user can manipulate or explore later using VR headsets and lenses. Displays, optical systems, and cameras are important here. Another area that's generating a lot of interest is 3D laser manufacturing. Lasers can be used to build cars or robots through cutting and welding. They can be used for 3D printing via stereolithography, in which a laser is used to cure a photosensitive resin, thus making a 3D solid. This can be used from everything from toys to models to complex optical parts that are manufactured today. Metal powder bed fusion printers use 500-watt lasers, whereas those used for cutting can be in the kilowatt range. Finally, let's talk brains and stars. If you want to image the asteroid that may take out Earth, you need a telescope which images light from faraway objects onto a detector or a camera so we can study it further. Do you like those fantastic images that are coming back from our latest telescope? This is an example of a fabulous imaging instrument that's produced rich amounts of data for science. Now, let's zoom into really small objects. As mentioned earlier, your brain is an amazing piece of hardware that we haven't yet been able to emulate. By using fluorescent markers that either emit light when a neuron is stimulated or when it activates, one can study the interplay of these fascinating objects. They hold the key to many complex mysteries, including learning, memories, and unfortunately, neurological disease, such as Parkinson's, Alzheimer's, and PTSD. By building miniature microscopes to image the brain under realistic conditions, much information can be learned and used to improve the quality of life as we know it. In summary, I've told you about a number of exciting applications and areas that are impacted by semiconductor photonics, semiconductors, solar power, laser, 3D manufacturing, and microscopes and telescopes. I'd now like to give the floor to Alan, the course facilitator for the Semiconductor Photonics Graduate Certificate. He will discuss the optical engineering specialization.
Thank you, Professor. Now I'll talk about the exciting field of optical engineering. This series covers 3 topics: first-order optical system design, optical efficiency and resolution, and design of high-performance optical systems. The purpose of studying optical engineering is to gain experience in the design, development, and optimization of optical systems and devices that manipulate light. This multidisciplinary field combines principles from physics, engineering, and material science to create innovative solutions for a wide range of applications, including communication, imaging, sensing, and display technologies. The study of optical engineering provides a foundation for understanding and development of various optical systems and devices, while its connection to the semiconductor photonics enables the creation of advanced, efficient, and compact solutions for a wide array of applications. In the first course, first-order optical system design, we'll begin by exploring light in a laboratory setting, illustrating how it can be understood as a bundle of rays. These rays may reflect off a prism or refract through a glass block, and by combining the glass blocks or prism, student can create the most basic lens. Using simple trigonometry, we will derive the properties of lenses and optical systems, allow us to analyze and design them for a specific purpose, such as magnification or imaging. Once we establish these first-order designs, we'll examine their performance with real glass and under real operating conditions. We'll incorporate actual glass designs into Zemax Optical Studio, a software that will be available to you, which enables the simulation and understanding of complex optical systems like zoom lenses. We'll analyze spots formed on an imaging plane and optimize the configuration based on the desired application. The process of optical design starts with first-order principles, followed by basic calculation to define their desired functions, derivation of the lenses that achieve those functions, turn them into real optical systems, and again, optimizing performance using software like Optical Studio. Mastering these skills could lead to a career in an exciting laser lab, where you will have a deep understanding of components like beam splitter, and lenses. Essentially, you can start design an optical system on paper first, then using value tracing on Excel sheet, and eventually optimize the design with Optical Studio and begin turning these designs into real-world imaging systems. Next slide. The second course of optical efficiency and resolution emphasizes the finite size of optics, focusing on 2 elements, the aperture and field stop, essential for designing optical systems. We'll examine 2 critical rays that describe how these stops functions and learn about the crucial properties of finite optics, such as field of view and resolution. This knowledge will enable us to solve the problems like designing a black box optical system to transfer light from a light bulb to a projector, which might be used in a digital cinema system. The efficiency and resolution of the optical system design from the first course can be better understood through techniques learned in this course. In the design of high-performance optical systems, the student will dive into the imperfections of optical systems and learn how to enhance real designs to achieve desired performance. We'll explore various aberrations, their causes, and methods to minimize them. For instance, chromatic aberration arises due to the variation of a lens, this refractive index with wavelengths, resulting in multiple focal points for different colors. We'll visit the lab to observe these effects and discover techniques to reduce such aberrations. Utilizing tools like Optical Studio, we'll calculate the contribution of each surface in complex optical designs and minimize aberrations through numerical optimizers. And specific design techniques will also introduce components beyond lenses, such as prisms and diffraction gratings, and learn how to incorporate them into designs using Optical Studio. Upon completing the optical engineering specialization, The students will be able to demonstrate a strong understanding of geometric optics and first-order optical system design principles, enable them to analyze and create basic optical systems. Utilizing Optical Studio software proficiently for simulating, optimizing, and enhancing complex optical systems, preparing them for practical applications in the field. Students will also apply the knowledge of finite optics properties, such as field of view and resolution, to design efficient and high-resolution optical systems for various applications. The student will be able to identify different types of aberrations and their causes, and employ techniques to minimize these imperfections to improve performance of optical designs. Integrating additional components, such as prisms and diffraction gratings, into optical designs using Optical Studio, and expand range of possible optical systems configurations. Now I'll turn the floor to Erica.
Thank you, Alan. I am going to talk briefly about our revolutionary program and how it differs from the traditional school system. A traditional on-campus graduate program requires an application process. Our program, on the other hand, is performance-based admission, so no application required, which means no GRE scores, no TOEFL, no IELTS, and no letters of recommendation. All you need to do is to prove that you can do the work by completing a series of courses in a pathway specialization with a cumulative GPA of 3.0 or higher, which is about a B average. And that qualifies you to be admitted into the degree program as a graduate student at the University of Colorado Boulder. Now, each course in a traditional program consists of 3 to 5 credit hours. In our program, each course consists of bite-sized 0.6 to 1.2 credit hours. And in order to get admitted, you will need to complete a series of courses called Pathway Specialization. And then we have, in a traditional program, there are normally 3 semesters per year. Each semester is about 16 weeks long. Our program, on the other hand, runs 6 sessions per year. Each session is 8 weeks long. Traditionally, students pay per semester, which can be quite expensive because you have to pay up front. Conversely, in this program, you pay as you go, and the tuition fee is $667 per credit hour. Now, what will admitted students receive? First, students in the MSEE on Coursera program earn the same credentials as our on-campus students. There are no designations on the transcript, certificate, or diploma to indicate that this is an online program. The students will have earned a fully accredited Master of Science in Electrical Engineering or graduate certificate. In addition, students who have been admitted into the degree program will receive a lifelong access to Handshake, which is a career-seeking tool offered through CU Boulder Career Services. Handshake is a place where employers post jobs, as well as serving as a social network to connect with fellow alumni, including the weekly virtual employer events. And finally, the CU Boulder Graduate School applies to admitted students, so such as policies include course repetition, grade replacements, academic standing, and so on and so forth. Overall, by reducing the time commitment and the number of credit hours per course, students can earn the same rigorous degree or graduate certificate without the intensive 16-week long commitment that traditional programs require. And to learn more about a program, Carly will put the website on the chat, which she has. So thank you, Carly. And that sums up our Semiconductor Photonics Graduate Certificate presentation. We are now ready for Q&A, and Carly will be our reader.
Thanks, Erica, and thanks to our panelists for providing some information about our degree programs here at CU Boulder. So I'd like to start off a question for the entire panel here. If you could tell us a little bit about how your courses compare, or how they're comparable to the on-campus version, and if you would find this maybe harder or easier. Let's start with Juliet.
So I actually really wanted my on-campus class to translate to Coursera. And so I think that I have been successful in that. So I think my Coursera active optical devices specialization is quite challenging, but I also believe that, you know, the challenge will allow you to gain a lot of knowledge. Thank you.
Do you want me to go next?
Yeah, Juan, go ahead.
Okay, so both my semiconductor devices specialization and quantum mechanics for engineering specialization are very similar to the on-campus courses that I teach. The lecture material, I would say, are almost the same. The pace of the lecture is slightly different because the Coursera is a pre-recorded lecture, whereas the on-campus lecture is a bit more interactive, but the materials covered are identical. I think the depth is almost the same. That's what I would say.
And Alan, any comments from the student perspective on the level of these courses?
I'll talk about the optical engineering course. The on-campus student also uses a Coursera platform to do the homework. It's basically the same homework question. And in terms of difficulty, this is a really good question. It can be easier or harder depending how much time you want to spend investigating the subject and how spread out your study takes. The course is currently offered at 8-week sessions, and you can audit the non-credit version before you sign up for the actual course, which means you already have a head start to begin with when you enroll in the program.
Great, thanks. I think that is a good jumping off point to our next question here. So what would you recommend for someone who already has an undergraduate degree in electrical engineering and wants to start their graduate program in photonics? Do you have any advice on how to better prepare for the start of classes?
I think the question is for me. So I will highly recommend the student to first audit the course for the non-credit version and go through the lecture materials. And if they're interested enough in the course material, then they can sign up for the full credit version.
Great, thanks, Alan. So this one here, I'm going to start with one on it. Can you tell us what materials or prerequisite courses you would recommend for someone interested in the certificate coming from a background in a different engineering specialty?
Yes, so I think the critical sort of background materials are math. So specifically some linear algebra, you know, basic engineering math. That will be a critical skills that's needed to be successful. Other than that, I think most of the lectures are designed to be sort of self-contained. We provide the materials that we cover the materials needed for in-depth understanding within the lecture. So if you come with a solid foundation in basic math, I think that's all you need.
And
go ahead, Alan.
And for the certificate, general undergraduate courses in physics, calculus, multivariable calculus, differential equations, modern physics, electromagnetism, quantum mechanics or quantum physics, and thermal physics and semiconductor physics will be very useful.
Great, thanks. Anything to add on that, Juliet?
You just need to bring a willingness to learn and be challenged.
Excellent. Thank you all. So the next one, I actually want to target Juliet, you again on this one. Can you expand more for us on the chip shortage issue and what we can expect in the job market?
So, I mean, the US has, for many years, in my perspective, not really invested in semiconductors. You know, I run a photonics research group, and if I want to buy a laser, particularly a semiconductor laser, I don't start looking here. I start looking at companies in Europe, and that's a direct result of people not investing in these technologies here. It's also true in a more general sense in terms of the electronic chips that people noticed were in short supply. You know, we've watched a lot of the manufacturing of these chips. We've watched the plants be closed, at least in the US, and it be exported to other places. And then not only that, really consolidated. And so, you know, if you're just looking at, for example, Global Foundries and TSMC, you know, it's really not enough. And so the CHIPS Act, at least in the US, is supposed to revitalize that industry. The other major comment I want to make is, you know, when I went to school, we had a full 10-week course on semiconductor physics. And when I came here, the first thing that happened was they said, well, this has gone out of fashion. And so they removed that requirement, as electrical engineering programs around the country were doing. And it's very clear, you know, as I mentioned in the short talk I gave about the CHIPS Act, that there is also support for STEM education and workforce development. And so I think that's actually why the Semiconductor Photonics certificate is so exciting, and it comes at such a relevant time. Thank you.
Great, thanks. So this next question is coming to us from an engineering student who is more interested in physics rather than engineering. So we'll start with one on this one here. Do you think that photonics is a great field for someone who wants to become both a scientist, a physicist, and an engineer?
I believe so. I myself is a physicist. I got all my degrees in physics. And I sort of found a passion in sort of the applied physics and the application of these fundamental science into useful applications. So that's why I found the position in an engineering department here. So the photonics, or semiconductor photonics to be specific, it's right at the junction between the fundamental science and a myriad of potential applications. It's a great place to be both scientist and engineer.
Great, thanks. Juliet, anything to add?
So I'm actually, my training is all in electrical engineering, but I essentially run a group in applied physics. And so I have both physics and electrical engineering students. And I would say at some level, you know, the interests merge. So I guess I really wouldn't be concerned. And I think you see that in the Semiconductor Photonics certificate. And that's actually really nice. You know, the world is becoming more interdisciplinary, and the more training you can get, the more marketable you are.
Great, thanks. Alan, I have a few questions for you now about the student experience and what you gained from your time taking your classes with CU on Coursera. Can you tell us what drew you to this program?
At first, I was at work. I had some questions that I had some projects I need to do that require semiconductor physics. So I came across Professor Park's course, and while taking the course, you know, the ROI was pretty much immediate, and enabled me to have more engagement with the project at work on a more technical level. And initially, I wasn't sure I was even able to pursue a degree in electrical engineering. And after taking more classes, I'm more confident about the process. With the support from the program staff and the TAs, and I was able to graduate in 2021.
Great, thanks. Another couple more questions directed here for you, Alan. So specific to the optical engineering specialization, how does the ZMAX software for non-credit students work? ZMAX software is currently available for students enrolled in for credit courses, and
only, as there are licensure restrictions. So for the student in the non-credit version, a free version of Oslo is available. Professor McLoy has updated the course with Oslo as an alternative software.
Oh, what a great tip for our non-credit learners. Thanks for sharing that information with us. So last question to keep you on the spot here. Alan, can you tell us what course was your favorite and why?
I'll say that definitely the active optical engineering course. I studied really hard for that course because it covers a wide range of topics based on, I think, 5 or 6 different textbooks. And I really enjoyed going through the materials. And actually, it's a course I learned the most in terms of putting all the concept together from optical engineering and semiconductor physics.
Great, thanks so much. So I'm going to pivot back to Juliet and Juan here for you. So learning these subjects generally requires access to expensive hardware and labs. How do you deliver this or an effective course without access to real hardware? Juliet.
So I can take a crack at this. It turns out that while there are lots of lovely things to do in the lab, you first have to understand the theory, and there is a lot of theory to understand. So my course is really laying the theoretical foundations so that you could go off and design something and then like learn about the fabrication and put something together in a lab.
Yeah, I would echo that. I mean, both my specialization, semiconductor devices, and also quantum mechanics for engineers are sort of foundational courses. It sort of lays the foundation for more advanced concepts or topics. So I think for those specialization especially, and for others probably too, the focus is really understanding the concepts and have a firm grasp of the physics and the basic principles rather than building something. I think that will come naturally after you gain these foundational knowledge.
Great, thanks. I think we've touched on this one a little bit earlier in our Q&A, but I do want to bring it back just because it was an important question from our audience today. So what is your recommendation to get prepared for this program as far as math, physics, and engineering?
So I think, I think this was stated by Juan and also by Alan. The mathematical background is absolutely critical. And I think, there are many ways that you can have that, the mathematical background, the physics background, I think is important. And then, like a willingness, as I said, a willingness to go after it and realize that learning doesn't come for free. It takes a lot of work.
Yeah, so I already mentioned that the basic math will be the critical skills here needed to be successful in our courses. If you have general physics background, that should help. Like the college, undergraduate level college, introductory physics course, that sort of thing should help. But again, I mean, if you watch our lecture videos, we try very hard to explain in these basic concepts before we throw at the audience. So I think those math skills, to me, more like a language skills. You got to be able to speak the language. If you have that, then I think you will have the ability to properly communicate in these specializations and understand and learn the critical concepts that we're trying to convey.
Great, thanks. So are classical optics or semiconductor manufacturing, such as lithography, EUV, covered in this specialization? A question from the audience there, so hopefully I didn't butcher those pronunciations too much.
So I do touch upon that in my semiconductor devices specialization. I do not go in depth in describing the details of lithography process, but in discussing CMOS devices, introducing the basic device structures and how CMOS works, I do touch upon how they are fabricated through the standard lithography process. I do not mention deep UV process specifically, but they basically operate in the same principle. They simply use shorter wavelength.
So I'd like to add to that. So the semiconductor course covers the fundamental principles that you can use laser or light to make the features that you need for semiconductors, and you basically need to understand the physics behind it and how it interacts with lasers. And optical design course that discuss the reduction of aberrations, distortions, when you're pushing the limit of imaging resolution. There are specific techniques in mask design that can enhance the feature resolutions that can be better understood once you take the optical engineering course.
Great, thanks. So as we're getting towards the end of our Q&A session, I do have a few wrap-up questions here to ask. I'm going to start with Juliet and Juan here on this one. Can you tell us a little bit in kind of a final wrap-up? I know we've touched on it a few times, but just great to hear as we're getting ready to end our time together today. What drew you to bringing your Coursera's from the classroom to Coursera, and maybe what ideas or opportunities you have for your specialties in the future?
So as I mentioned, I'm a 5th generation engineer, and I've actually become very interested recently in being able to share my knowledge and my skills with others. And I am really motivated by this idea of being able to give back and being able to empower people who didn't have the kind of opportunities that I had. And I think I think this is a way to actually increase diversity in the specialization. So I think it's just a wonderful idea that we can actually do this and execute on it. And as far as other specializations in the future, I guess for me that's still to be determined. I'm toying with the idea of writing a textbook to go with the active optical devices, but haven't quite decided.
Great, thanks.
Yeah, for me, these semiconductor physics or semiconductor device or photonic devices are the topics that I got excited about a long time ago. I decided to build a career on it, decided to study, make a career studying those things. So that's has always been my passion. I enjoy studying them. I enjoy teaching them. So when the opportunity came to sort of make the course available more widely through Coursera platform, I jumped on it. And it took a long time. It took a lot of work, but I think, seeing these courses reaching a great many number of students, I think that's my satisfaction, and I hope I can continue. I don't have any immediate plan to offer more courses on Coursera, but I'm hoping to be able to find time to offer more courses in the future.
Great, thank you both so much. We did have a last question here come in via the Q&A. So hopefully Juliet or Juan, one of you will be ready to tackle this one here. Is it possible to have any interaction between silicone and acetone?
I am not sure what you mean by interaction between silicon and acetone, but in a conventional, typical lithography process, silicon is patterned using a photolithography process. And in that process, we use a photopolymer called photoresist. And those photoresists need to be removed after all the device fabrication process is done. And that resist removal process typically uses acetone. Silicon is not attacked by acetone. And acetone attacks these polymer material that we have used to pattern silicon. So that's the typical relationship where the typical context where silicon and acetone are used together.
Oh, great. Juan, thanks so much for jumping in to tackle that last question from the audience here. Before we end our Q&A part, I guess, Alan, any final passing thoughts from that student experience that you had within our program or from being a course facilitator that you'd like to share with our audience?
So for me, it's a wonderful experience because the material I learned challenges me, and it definitely made me a better engineer, and it prepared me well for my current role when I started to transition to when I tried to make a career change.
Great, thanks. And thank you to all of our panelists today for your efforts here in our Q&A. We really appreciate you taking some time to answer questions from our audience, and I'll turn it back over to Erica.
All right. Thank you, Carly. So we have come to the end of this webinar. I'd like to thank Carly for being our reader, and thank you, Adam, for answering the Q&A. And of course, I'd like to thank our presenters, Professor Juan Park, Professor Juliet Gopinath, and Alan Su for your time. Thank you, thank you. And if you have additional questions, please email us at msce-mooc@colorado.edu. And thank you again for joining. We will send the link to the recording next week, and have a great rest of your day.